I think it's fair to say at this point in the course that we've been on quite an adventure. We've managed to visit all sorts of far-flung, exotic, and interesting destinations all throughout the world of algorithms. But for me at least, any trip can get exhausting after a while, and from my end, I think it's time to come home. Here is a topic that I have been looking forward to since the very beginning. And honestly, every single time I teach an algorithms course, I walk in on the first day of class and I think to myself, I can't wait until we get to talk about graphs. Graphs are the reason that I am an algorithms person. They fundamentally are the reason behind why I teach algorithms courses, or frankly, why I got into teaching in general. And I think this is a good moment to reflect a bit, as I did in lecture 19, when we talked about red-black trees, about my experience as a student. So back in lecture 19, I talked about how when I saw red-black trees as a student, and they came up in a few different places, red-black trees and other self-balancing binary search trees, I seemed to always walk away from the experience feeling a bit intimidated and maybe frustrated by the material. I wasn't really comfortable using them. And I eventually became so I eventually did understand them. And looking back, it seems like what the problem was that every time they were presented, it amounted to being shown some slides that said, oh, just perform this operation by doing this stuff, like twist the tree around like this, and now you're done your insertion, or now you're done your removal. Now go and memorize these transformations and be prepared to do it on the exam. And then once you get a good mark on the exam, I guess you must know about red-black trees. And thinking, as a student, okay, I can go and memorize these. And even in cases where you can get the answer by memorizing something, it can be quite frustrating to produce answers from memorization. Because since you don't have a deeper understanding, unless your memory is absolutely perfect, you know you're going to get the answer wrong. But one way or another, because that's what happens when you're a student, you sometimes have to memorize stuff for an exam. I did that, and I passed the course, and whatever. Everything worked out fine. And as I mentioned in lecture 19, the problem was I was still rather intimidated and uneasy by that topic afterwards. It doesn't matter that I passed the exam, it matters that I wasn't really able to get what I was supposed to get out of that topic. And in lecture 19, I talked about how, it's unclear exactly who's to blame for that, but a lot of it did seem to come down with the way it was being taught and the person teaching it, the instructors that I had. It felt like since they were just presenting it as, here's a bunch of stuff to memorize, now go memorize it, either they didn't care about the topic, or maybe they themselves didn't really understand the topic well enough because they were intimidated by it too, or they just didn't know the topic and didn't care that they didn't know about it. I suppose it could be some combination of those two things. And so what that meant, if they were also a bit uneasy with the topic, is that they wouldn't want to describe the topic in much detail, and they may not have been able to generate explanations beyond, here are the operations to perform. I thought a bit after recording lecture 19 about that experience, and I thought, was I ever given an explanation of how the red-black tree or how the self-balancing tree worked? And I realized that to the extent I could remember any specific explanation being given, it usually amounted to sort of somebody reading the textbook to us. That is, it didn't seem to synthesize any new information. And that is consistent with the case where maybe the instructor was a bit uneasy and they were concerned they couldn't give a good explanation or they didn't know a good explanation. Now, there are lots of reasons for that. I mean, that is, when you're a teacher, even if you do know the material really well, it can often be very difficult to explain it, and it's hard to have confidence in that. That's an example of something I think, that's an example of something called imposter syndrome. And this is something that I think everybody in technical fields faces every now and then. So imposter syndrome is the unwarranted feeling that even though you are objectively an expert in your field, you feel like actually you don't know anything, and that it's only a matter of time before somebody figures it out and they expose you as an imposter. And I'll bet that you've experienced this, that although objectively you do actually know a lot, and you likely have experience in your background to prove that objectively, there might be days when you get up or you will get up in the future and you go to your job as a software developer or as a professor of computer science or whatever, and you think, actually, I don't know anything. And it's a miracle that I've made it this far without anybody noticing that. I think that's very common in technical fields, especially because usually you have colleagues or peers that also have to make sure they give the impression they know stuff. So everybody is sort of worried that they're pretending they know stuff, even though they all actually do know stuff. And so when you notice that your peers seem to know what's going on, you're worried that actually deep down you don't, that you're actually an imposter. That's imposter syndrome. And it happens just as much to educators as to anybody else. There are topics where I occasionally catch myself worrying that even though objectively I obviously know about the topic, do I really know it, or have I just memorized stuff? Or am I just lucky that nobody asks me certain questions? And so it could be that my instructors long, long ago had the same problem. They were worried about how they were describing a topic, and so they sort of were freaking out a bit and decided not to give a long explanation because they were afraid they might say something that was incorrect that would expose them. But for one reason or another, I walked away from discussions of things like self-balancing binary search trees not quite sure that I understood either, not quite sure that I had the pieces necessary to really make sense of the topic. And that was too bad, and it frustrated me for a long time afterwards. And that's something that, with any learner, whether it's the instructor's fault or not, can be very frustrating. But so now I've just said all these, I've made these reflections that may reflect negatively on some of the people that taught me. And I don't take them back. I stand by them, but I do want to make sure I take the opportunity to also give a positive version of the same reflection. So although there were some topics, not just red-black trees, where I felt like in my educational experience, somebody dropped the ball. And I think textbook writers in some cases often describe topics. I don't know if red-black trees are one of them, but a topic we'll talk about later in this course certainly is, and I'll talk about that when the time comes. Sometimes textbook writers drop the ball as well, and they give a description of a topic that makes no sense or is so vague that it's impossible to use it. That's very frustrating. But there was one topic, and it was graphs, where honestly, and I thought a lot about this before recording today, everything I reflect back on, every experience I have of taking a course that involves graphs had the exact opposite than my experience with self-balancing binary search trees. So whether it was taking a discrete math course taught by an expert in graph theory or an algorithms course taught by an expert in graph algorithms, and I liked graphs so much I eventually took higher level courses, effectively elective courses in graphs and graph algorithms, and of course those were taught by experts that knew what they were talking about and loved their subject. So of course when they taught a course you could tell they loved the material and they cared about it. But even if I took a course from a computer networking expert that had to use graphs occasionally in their line of work, or just somebody teaching a course that covers graphs for 1 or 2 lectures, every single time that I took a course that involves graphs, the instructor teaching it, regardless of their background, always projected an air of really caring, not just that we understood that a graph could be used for this problem, not just having us memorize some transformation for the exam, but they really seemed to care. They really seemed to take it personally that not only did we understand the operation being performed, that we understand why a graph was a useful model for that operation, why it was an efficient way of thinking about that task, why it was an elegant and beautiful way to think about that task. And that stuck with me. So I saw graphs a lot of times, and you probably have already seen them in some context. You'll likely see them in both discrete math and computer science contexts. They are one of those topics that's one of the most transferable things from a course like this. There are lots of things in this course you're going to need later. Depending on exactly what path you follow, you might need some things more than others. There are in fact some topics we've covered that if you follow a certain path after this algorithms course, you might never need them again. I will admit that. But graphs are not one of those things. Graphs are something that pretty much any path you follow out of this course in a field like this will take you into some need to use graphs, whether you use them for the context of designing graph algorithms or analyzing them or implementing them or just using graphs as a model for things, I don't know, but you will need graphs. They are a really big deal. And for me, I think back on moments as a student that did change the trajectory of what I studied and my career overall afterwards, and graphs factor into all of them. There's one specific moment that comes to mind when I think of a sort of light bulb moment for myself, and I'll refer back to this more in a couple of lectures when the same algorithm comes up in this course. But when I was taking the equivalent of this algorithms course long ago in a classroom in the basement of some building somewhere, I remember vividly one specific moment where a particular algorithm was presented, and it was a graph algorithm, and I was in complete awe. This operation that I had been thinking about for like projects I was working on or assignments I was doing for a long time turned out to boil down to an incredibly simple, efficient, and elegant thing as long as I chose to think about the problem in terms of graphs. And that was amazing. And it is very likely that that one moment, stemming from that one moment, was the reason that I went on to study algorithms, to study graph algorithms, to become a graph person or an algorithms person, and ultimately to begin teaching computer science. A lot of stuff stemmed from that one moment. Okay, so hopefully the reason for things like that, for what I just said, for why graphs always seemed like something that was tangible and elegant and interesting, and it always seemed like the instructor cared, hopefully that's just because graphs are great. Maybe because graphs are so great, even the most jaded educator that cares as little as possible has no choice but to cover graphs in a way that is engaging. Certainly, if that's the case, that helps me out a lot in these lectures. But in any event, graphs are something that I think is very important that people understand, not just because you can memorize some operations for an exam, but because if we learn to use graphs, to adapt them as models for things, and to use the algorithms that come with common modeling with graphs, we can do a lot of really powerful stuff, and it is pretty natural. Okay, so I think that it goes without saying that graphs are a big deal in this course, and I really like graphs, and so if you found my enthusiasm for trees over the 7 lectures we talked about trees, if you found that to be insufferable, I'm afraid that was just the warm-up act, and we're going to spend a lot more than 7 lectures talking about graphs. So we've got a lot to talk about. We've got no time to lose. So let's get started. But actually first, I would like to talk about a geography problem. So there's this river, and it's currently called the Pregolia River. In modern day, it flows through modern day Kaliningrad, which is in western Russia. And you can see here, I've zoomed in on a certain part of the city. Notice how the river branches out a bit, and it divides the city between 4 different land masses. So on the top, we have the north bank of the river. We also have the south bank of the river. Obviously, this thing here is an island in the middle of the river. It turns out this mass over here at the upper right is also an island. It's just that it's so big that it runs all the way off screen. All right, so that's very interesting. But the problem I want to talk about doesn't relate to modern day Kaliningrad. It relates to the same city 300 years ago. So in 1736, well, more or less 300 years ago, the city was called Konigsberg. And at the time, there were these 7 bridges that crossed the river. Now, of course, today, there are still plenty of bridges crossing the river. I believe, although this is non-authoritative, I believe that one of the bridges may still be one of the ones. Maybe 1 or 2 of them are the bridges from back then. But I think many of them are modern bridges carrying like freeway traffic, and there's probably lots of other bridges too. But back in 1736, there were these 7 bridges that crossed the river and connected the different land masses. Now, also true in 1736 was that with one's limited leisure time back then, there wasn't very much to do. You couldn't really use the internet or watch TV or anything else. And you couldn't listen to music unless you happened to have instruments lying around, or you could afford a ticket to the symphony if that existed. I don't know. I guess classical music would have existed back then. Who knows? So suppose that in your leisure time, you decide to go for a walk in Konigsberg, and you're standing here. And, going for a walk can be sort of interesting, but you've been there forever because back then you couldn't just hop on a plane and travel. You didn't have cars either. That's why you're going for a walk. And so after a while, you begin coming up with challenges that you set yourself. And one challenge you want to think about is the question of, is it possible to take a walk in Konigsberg that crosses each of the 7 bridges exactly once? So certainly I can take a walk that crosses all 7 bridges. Let's try this one here. I walk across these 2 bridges, I turn around and walk across these 2 bridges, I turn around and walk across this bridge, and I end up back here. And I realize if I want to get to the last remaining bridge, I have to cross a bridge I've already crossed. That's too bad. So this particular walk wasn't able to cross all 7 bridges without crossing 1 bridge twice. Okay, maybe if I try again, I could find one. Okay, let's try, I don't know. We'll start here again. We'll walk over this bridge. Then we'll do this one. This was the problem last time, so we'll do this one early. Then I walk back up and I do that. Okay, now I'm stuck again. So I can't get back up there unless I cross a bridge again. So maybe I backed up and I go over this one and then down here, and then I go back over here, and I see again that it doesn't seem like I can get to that 7th bridge. But maybe I'm just trying wrong. Maybe there's some trick I don't know about this problem. And so that's the question. Is it possible to take a walk in Konigsberg in 1736 that crosses each of the bridges, but it crosses every bridge only once? I never have to cross a bridge twice. This was actually a bit of a big deal at the time. And so this walk here on the slides is crossing 6 of the bridges. And you can see that once I'm finished my walk, I end up with this bridge left out. And there seems to be no way to get back to either of the 2 land masses that the bridge connects without crossing over a bridge a second time. It turns out that this problem was studied by none other than Euler. Perhaps you recognize that name from somewhere. And so it came to the attention of somebody that probably could actually help solve the problem. And Euler noticed one key aspect of this problem is that the actual thing we're trying to find is very limited compared to the amount of information that we have. We could reduce this to a very abstract problem with much less meaningless, useless information. So the question of, can you take a walk that crosses all 7 bridges seems to be a question of, if I start anywhere and I follow any path I want, is there some path that crosses all 7 bridges? But I realized later that I don't really care the specifics of what the path does except when it crosses bridges. I do, of course, care, like if I call this landmass A and this landmass B, obviously I care that if I cross from landmass A into landmass C, that the next bridge I take has to be one of the bridges that leaves landmass C. There are certain constraints, but I don't care that much about the specific contours of the problem. So one observation is the only relevant information in a solution, so a possible walk, is the order in which the bridges are crossed. There are certain orders that don't make sense. So for example, I can't cross this bridge in this direction and then immediately afterwards cross this bridge, because how would I get between the two bridges? It does matter what order they're crossed, and there are certain orderings that are allowed and certain that aren't, but nothing else about the path really makes a difference as far as the solution. I don't care about the river, I don't care about the islands, I don't care about whether I walk directly between these two bridges or whether I take my time and walk all over the place in the meantime. I just care about the bridges themselves. So for example, this path here and this path here are basically identical as far as the question of the 7 bridges is concerned. So one of the things Euler noticed was that we can abstract this problem into a much more simple form. And what's also neat about this, looking back on it from 2025, is that the thing that he did that's so clever isn't as clever from our modern point of view, because modern mathematicians are experts in abstraction. Now, to be fair, mathematicians of Euler's time were good at abstraction too, but we take a lot of abstractions for granted, especially in computer science and math, because we've had all this education that has trained us to be able to abstract problems. What Euler did at this point was considered pretty amazing, because it was a technique that, although others had used it, it helped to formalize the idea of boiling a problem down to its most basic elements that we need to solve it. So, in general, the movements that we make on a particular landmass are irrelevant. All I care about is, if I cross this bridge, I eventually get to this bridge here. Whether I wander around in the meantime doesn't make any difference unless I'm crossing bridges. So what I could do is I could collapse down each of my landmasses to a single point. So I could just represent each landmass by one point, with the idea being that once I get to a landmass, it doesn't matter what I do internally, so I don't care that the landmass has a large area. And then I think about the bridges and realize that I don't even care too much about the bridges themselves, I just care about which landmasses they connect. So what I could do then is represent each landmass by a point and each bridge by a connection between those 2 points. So in this case, what I do, for example, is I connect these 2 landmasses here by this bridge by just drawing a connection between them, a link between them, a line. Now, I also observed that the actual location of the bridge on the map is sort of irrelevant too. I mean, that is, yes, I drew this line to sort of match up with the location on the bridge, but I could clean up my diagram a bit and just rearrange it to look sort of like this. So here I have a cleaner diagram that I claim completely models the problem of whether I can cross 7 bridges. Now, I want to come back to this later and talk about how Euler solved this problem, but notice how we have eliminated a ton of irrelevant detail. We don't care about the river, we don't care about things like how long the bridge is or how wide it is. We just care about the connections and walking between 2 landmasses. We've modeled the landmasses, we've modeled the bridges. Each landmass is modeled by 1 point. Okay, but if you say something like point, people don't think you're as smart or clever. We want to use some crunchy mathematical terms. We're not going to say point. That's not going to get us taken seriously. We're going to call it a vertex. And we're going to represent the bridges by connections between pairs of vertices. And we'll call these things edges. Now, the discipline of graph theory, I think, might have inherited these terms from the fact that a lot of early uses of graph theory tied into certain applications of geometry, like the study of polyhedron and things like that. And those had vertices and edges, and I think that might have been where we got these terms from. So Euler was able to reduce the 7 bridges of Konigsberg down to this representation of vertices connected by edges. And he published an article about this, and here is the diagram from his publication that I was able to find on the internet somewhere. He published this article. He was an academic, so of course he has to publish articles. He published it in Latin. That's definitely going to impress the tenure committee, although I don't think tenure was invented until about 180 or 200 years later, but certainly that would be very impressive. I hope Euler got tenure, and we'll never know. And Euler's article is considered to have founded the study of graph theory. Now, as it turns out, graph theory came into its own as a discipline, and by my reckoning, probably around the 1950s. That is, certainly graph theory existed before the 1950s, and we consider Euler's article as having founded it, but it didn't really take shape as its own subfield until somewhere in the mid-1900s. I'm going to pin that down into around 1950s was when people began writing books on graph theory. Some of the fundamental books about graph theory were written then, and that's why some of the terminology we're going to see about graph theory seems to date from that period of time. So what's a graph? I guess that's our next question. A graph is a mathematical structure that models pairwise relationships. So it's a collection of vertices. So here are our vertices. And then the vertices can be connected by edges. And an edge represents a connection between a pair of vertices. Now, when we think about a graph as a mathematical concept, although you'll find that I like to draw graphs in this representation, I visualize them with a vertex drawn as a point. I draw the points as very large things because that way I can give them a name if I want to, and edges drawn as lines. Fundamentally, a graph mathematically is a pair of two sets, a vertex set and an edge set. That's all it is. It has no inherent notion of position or distance, which means my choice to draw the graph like this is my own. That is, I could draw this graph in a lot of different ways that model the same collection of pairwise relationships. And so notice how because these connections connect two vertices together, that's a pairwise relationship. The edges model relationships between vertices. Now, although a graph is a set V and a set E, sometimes we find that we're talking about more than one graph at a time. And in those cases, I will use this notation to refer to the vertex set and edge set of a particular graph. So V of G and E of G. I may use just V and E in certain contexts, but to be honest, I tend to like using this in all contexts because when we get to talking about things like pseudocode, there can be ambiguity and it's better just to completely avoid that. So each edge in my graph is a pairwise relationship, and it corresponds, that's a bit of a loose term, I will define that more carefully in a minute. An edge corresponds to a pair of vertices in V. So here I've given this edge a name, we'll call this edge E. Notice that E corresponds to the pair U and W. Also notice that there's nothing else represented by that edge besides that U is somehow associated with W by this edge relationship. There's no inherent directionality or hierarchy to this edge, it just connects U to W. And so in this case, because the edge itself is a simple connection between two things, where the two things are regarded as equal, we call this thing an undirected graph. And the reason we say undirected is that an alternative representation, so suppose I call this vertex A and this vertex B, if I want to represent that there's like a one-way connection from A to B, so from A to B, I'll put a direction along the edge, and we would call such a graph that has directions on the edges a directed graph. But the edge we have here, the edges we're working with on this graph, on this slide, are undirected. All they are is simple connections between vertices. And because they're simple connections with no inherent ordering, we can actually classify the edge object as itself mathematically as an unordered pair. So an ordered pair, like a coordinate pair in the plane, like an XY pair, might look like this with round brackets. Because it has a first element and a second element, and the order of elements is significant, because if we're representing points in the plane, then obviously if I swap the x and y coordinate, I have a different point. An unordered pair is just two things with no inherent ordering. If we use set brackets for that, we're just talking about a set of size 2. We know that a set of size 2 just has some members. It doesn't have the members in any particular defined ordering. It turns out that what I'm about to say is implied by the definitions I just gave, but to be clear about this, in this course, all of the graphs we will study, unless I say otherwise, occasionally we'll see examples of one of these things, but unless I say otherwise, all of the graphs that we study are what we're going to call simple graphs. In a simple graph, this is not allowed and neither is this. Specifically, there can be at most one edge between any two vertices. So I can have 0 edges, here's an example of two vertices with no edges between them, or between two vertices I can have one edge. I can't have more than one. Here are two vertices with 5 edges between the same pair of vertices. That is not allowed in a simple graph. Similarly, I am not allowed to have an edge that connects a vertex to itself. We might call that a loop or a self-loop. That is not allowed with our simple graphs. It actually turns out that the definitions I just gave require that. So this is actually implied by the definitions. I defined that our edges are a set, our edge set. And notice that if I'm allowed to have the same edge appear more than once, what I'm saying is that I've got, here's my edge is an unordered pair UW. It means in my edge set, I'm allowed to have duplicates. And of course, that's not allowed in a set. In a set, I can only have an element occur at most once. So this configuration wouldn't be permitted by the definitions I just gave. If my edge set was a multi-set that is allowed to contain duplicates, then this might be allowed. But the definitions we use do not allow that. Similarly, this can't happen because if I think about what this edge would look like as an unordered pair, it would be the pair UU. But remember that the unordered pair is a set, and that means that this is equivalent to a set of size 1. Because edges have to be sets of size 2, this wouldn't be allowed either. It's automatically ruled out by the definition. So both of these things are not allowed in the graphs that we are going to discuss. Now, hopefully you've picked up on a bizarre contradiction, which is that I just described graph theory from the beginning, talking about Euler studying the bridges of Konigsberg, and weren't the bridges of Konigsberg modeled with a graph that had this? Yes, I'm aware of that. That's a bit of a snarl. So this is not a simple graph because there are multiple edges between U and W, and there is an edge from U back to itself. And of course, the very first graph, as far as we're concerned, what we consider the inaugural graph of graph theory, the 7 bridges of Konigsberg, was of course not a simple graph. That's tough, I admit that. That's a bit of a, you're going to have to sort that one out on your own. What's interesting is, for our purposes, talking about algorithms, it's way easier to work with simple graphs because we only have to worry about edges either existing or not. We don't have to keep track of separate edges that otherwise are identical. That is, they have the same 2 endpoints. I'll define the word endpoint in a minute, but maybe it's clear what I mean by that. It also turns out later we'll discover that if we ever want to achieve this effect, we can do it with a more efficient representation for a lot of algorithms by using a simple graph. So I'll draw this. I'll try and make the drawing a little bit similar looking. So suppose I draw a simple graph that encodes some of the same relationships. So it has the same 4 land masses, but only one bridge is present. What we'll discover we can do in this course to avoid having 2 edges between a particular vertex is just tag particular edges to say, hey, there are 2 of these. So we can treat it like only one connection, but just keep somewhere the knowledge that there actually happen to be 2 edges. There are 2 bridges connecting these 2 vertices. There will be a couple of cases where we see multigraphs, and they are relevant in certain subfields. Ooh, what was that word? I guess I should fast forward here. So if I were allowed to have multiple edges between the same pair of vertices, I would have a structure called a multigraph. And we're talking about simple graphs in this course, not multigraphs. Now, as a student, when I first was given this restriction, when I was told, oh, in this course, we're only talking about simple graphs, but there are these things called multigraphs. I made the assumption that what that meant was that multigraphs were some kind of advanced graph that we'd get to eventually. Like maybe I take a 4th-year course that covers advanced multigraphs. What was weird was I took courses that involved graph theory as a 1st-year student and a 2nd-year student, and then higher up in the high level of my undergraduate years, I would choose courses that involved graph theory and graph algorithms, and then I did a graduate degree, and then I did another graduate degree, and basically never were multigraphs a big deal. That is, they came up every now and then, but they're mostly a technique we use to model certain problems. They're not necessarily any more advanced. They're just something that isn't necessary in most cases. So they can be useful. You might see them once or twice. We might see them occasionally in this course. But it actually turns out it's not like you get to some advanced level of graph theory where suddenly everything's a multigraph. There are subfields where they're more important than others, but they're not really that big of a deal in the grand scheme of things. Most of our fundamental graph properties, we can work with just simple graphs to achieve them, despite the fact that the 7 bridges of Konigsberg actually is a multigraph. Okay, so suppose we're working with simple graphs. Other than the fact that you're not allowed to have multiple edges between the same pair of vertices, there are no constraints on which edges can exist, other than, of course, the fact that an edge must connect 2 actual vertices together. So it is possible for a graph, here's an example of a graph, to have no edges at all. This graph has a bunch of vertices, but no edges. So often when we talk about edges, we can name the edge if we want to. So I can say, here's an edge called E. I can even name an edge even if the endpoints have no names. But usually I tend to take a pretty vertex-centric view of things, and I think that's common in the graph theory community. And so what I'll typically do is identify an edge by its endpoints. So I will I'll write out an edge not as an unordered pair because that's a lot of notation. I'll usually just use notation like this, UW or WU. In an undirected graph, an edge is equally the edge UW as WU because the ordering of the endpoints makes no difference. The edge is just a connection, a magnanimous connection between both endpoints. When I talk about the edge, I typically don't give it a name. I typically just, so if I have two vertices, there's A, there's B, I would just say consider edge AB. And the idea is edge AB is the edge that connects vertex A to vertex B. I guess we're a bit late in the sequence for this definition, but it turns out that if I have an edge that attaches two vertices together, those two vertices are called the endpoints of the edge. And the edge is said to be incident to the two endpoints. So the relationship between E and the two vertices U and W is that E is incident to U and E is incident to W. And U and W are the endpoints of the edge. Now, I want to talk a bit about the number of vertices and number of edges in a graph. Formally, the number of vertices is the size of the vertex set, and the number of edges is the size of the edge set. And actually, it does say that we will use this convention of using n and m, but I actually don't do that as much as the slide implies. It is very common in graph theory to see people always use n to represent the number of vertices and m to represent the number of edges. Originally, I had planned to do this, but at the last minute while making all the slides about the graph lectures, I went back and generally replaced n and m with these, because in algorithms where n and m can often mean lots of different things, it was just better to avoid ambiguity. But if you pick up a book on graph theory or graph algorithms and look at a random proof or something, you'll often see that they just talk about n and m without defining what they mean. And the assumption is always that n means the number of vertices and m means the number of edges. And I may use that in this course, but I won't use it as often as this slide implies. And you are certainly welcome to use it when you write exams or assignments or whatever, because it is a convention of graph theory. In this graph, the number of vertices is 12, and the number of edges is 17, just in case you wanted some confirmation of that. So a note about drawings. Normally, we choose, for the sake of making it clear what's going on, to draw graphs using drawing vertices as sort of single points and drawing edges as lines between them. Now, I like to draw edges as straight lines, but really edges could also be wavy lines for all we care. The key thing to understand, though, is that the graph itself has no inherent geometric interpretation. There are subfields of graph theory where that is studied. So there are generalizations of graphs where each vertex has associated coordinates. And there is, in fact, an entire subfield that studies how to draw graphs effectively, how to draw them with certain properties. And I've done some work in that field, and it's very interesting, but it's not the kind of thing we cover in this course. So the graph itself has no inherent geometric information or geometric interpretation, but we do choose to draw graphs in a way that's visually appealing. And I think that's sort of a point of pride for graph people. That is, if you're teaching graphs or using graphs, then it's sort of nice. It's a sort of point of personal pride that when you draw a graph, it looks very visually appealing. Because you'll notice in this lecture, and I have a very jarring example of it coming up in about 30 slides, you'll notice in this lecture that if the graph is drawn in a visually appealing way, a lot of properties that actually are pretty high-level, difficult properties to understand appear sort of obvious. That is, your brain, being the pattern-matching machine that it is, can look at a well-drawn graph and generate a bunch of very easy inferences using pattern matching. And that might make you think that certain properties that I make sound like they might be difficult to understand are sort of trivial. But really what's happening is the drawing is doing all the work for you. Remember that internally, if I think about what a graph actually is mathematically, so let's say our vertex set here, the vertex set for this graph is A, B, C, D, E, F. There's A, B, C, D, E, F. And that's it. And the edge set is this collection of pairs, the pairs AB, AC, AE, and so on. And if I just hand you these two things, that's a graph. And if all you have are these two sets, it's not necessarily easy to understand the overarching structure of the graph. It's only because I've chosen to draw it like this that the graph is something we can tangibly understand. So keep that in mind. Sometimes when things about graphs seem obvious, it's because the drawing is doing all the work for you. So the choice of how we draw graphs is arbitrary, although of course it's nice to choose a layout that people can read easily. But the choice of layout has no bearing on the actual structure, which is simply a collection of pairwise relationships. For example, this graph is the graph on the previous slide. I'm not saying it's equivalent to, it is. This graph and this graph are the same graph. They're just the same graph drawn two different ways. Most people would probably agree that this is the better drawing. There's just something about this drawing that looks nicer. One of the reasons is it looks much more, I don't know, symmetric, and it has a much more classical geometric flavor to it. One other thing I can observe is that this one is drawn with some edges where they cross over, which is fine because the drawing is arbitrary, whereas I found a way to draw this graph, or the same graph, such that the edges don't cross. But it's the same graph both times. I've just drawn it in two different ways. Because they have the same set of vertices and edges. If you look at the edges of both graphs, they are actually the same collection, and it's the same vertex set. It's just how I've chosen to draw it. And that is not a property of the graph itself, that's just a visual convenience. Now look at these two graphs. So on the left is the same graph as before. On the right is a graph that is different because the set of vertices is different. Instead of being A, B, C, D, E, F, it's V1, V2, V3, V4, V5, V6. So although the graph on the right does actually model the same pairwise relationships, the things that it's worrying about pairs of, it's working with pairs of V1, V2, V3, V4, V5, V6, means that it's not the same graph because the vertex set is different. And that means the edge set is different because instead of having the edge AB, we have the edge V1, V2. But on the other hand, they do model the same set of relationships. That is, I could convert this graph into this one pretty easily. All I have to do is change the name of each vertex. I call this V1, I call this one, I guess what was B? The B was V2, and so on. So we want a name for that. These two graphs are distinct, but they're similar enough that I can make them equivalent with a simple operation. Because it's possible to transform this graph into this one simply by relabeling the vertices, that means that G1 is isomorphic to G2. Two graphs are isomorphic to each other if you can obtain one from the other by renaming the vertices. So I can go from G1 to G2 or G2 back to G1 simply by renaming vertices, and that means that they are isomorphic. Okay, so more terminology about edges and vertices. So suppose I have two different vertices, U and W, and they are connected by an edge. The relationship between U and W in that case is we can say that U is adjacent to W, or W is adjacent to U. We can also say that U and W are neighbors. Now, hopefully by now you've noticed there's lots of terminology to learn, and this lecture is frankly mostly terminology. Just like with trees, and I hope you found this to be the case with trees, when we talked about rooted trees, there were tons of words to learn, but a lot of them were natural. That is, the idea of a tree as a hierarchy means that when we use words like parent and child, it's pretty easy to remember what they mean because they do seem to naturally map onto the structure. And I hope it's the case that much of the terminology we see today about graphs is similar. That is, when I talk about two vertices being neighbors, that is a pretty tangible thing. It makes sense that because they're next to each other according to an edge, that they are neighbors. And similarly, I can define the neighborhood of a vertex. Now, there are two ways I could talk about the neighborhood of a vertex. So because the neighbors of the vertex, if I look at vertex W, the neighbors are everything adjacent to W. And we'll call this set of things the open neighborhood. The open neighborhood, so N of V, where we use round brackets, that is simply the set of all vertices that are connected to a particular vertex by an edge. So the neighborhood of W would be, in this case I use N of V, so let's compute the neighborhood of W here. The neighborhood of W is going to be the set of all vertices U that are members of the vertex set, such that there is some edge UW in the edge set. That's the open neighborhood. And of course, the fact that I say open implies there is something called the closed neighborhood. So the open neighborhood is a set of all vertices adjacent to a particular vertex. But you stare at this and say, hey, wait a minute, we're talking about neighborhoods. I live in a neighborhood, but I'm part of my own neighborhood, right? Like if you're in a neighborhood, aren't you also part of the neighborhood? That's a good point. So we'll define a second variant called the closed neighborhood. The closed neighborhood of some vertex V is the set containing all of its neighbors and V itself. So W is part of its own closed neighborhood, but it's not part of its open neighborhood. Okay, so what about the number of neighbors? We call this the degree. The degree of a vertex, which we denote by this, and we use this all the time, the degree of a vertex is the number of edges incident to V, or if you want, the size of the open neighborhood of V. And I'll just use that as our formal definition. It is the total number of things connected to a vertex V by an edge. So if we look at the degree of this vertex U, the degree of U is 1, 2, 3. And if we look at vertex W, the degree of W is 1, 2, 3, 4, 5. All right, and the slides will hopefully confirm what I just said. There we go. The degree of U is 3 and the degree of W is 5. I don't know that we need this edge to be highlighted red, but there you have it. And we're ready for a theorem. So this is one of these fundamental theorems, and I believe it acquired this name around the 1950s. That's, as I said earlier, that's sort of when the discipline came into its own as its own specialized subdiscipline. It's 1930s through 1950s. It was used as sort of one of the various flavors of combinatorics up until then, but I don't think it came into its own until a period of growth that began maybe in the 20s and proceeded through the 50s. So we have this fundamental theorem that's really important, that's quite useful. The theorem is quite humble, so it calls itself the Handshake Lemma. Doesn't matter, it doesn't get to decide, I do, so I'm going to call it a theorem, but its proper name is the Handshake Lemma. Okay, Handshake Lemma, huh? Well, does that mean that it was named after somebody named Handshake? It never is with these things. No, apparently it was stated like this. Suppose that a bunch of people go to a conference together. Here are all the people, they're the vertices. And of course, this is in the 1950s. This idea of a handshake certainly dated itself pretty quickly in 2020. That is, in the course of a few weeks of 2020, the idea of calling this thing the Handshake Lemma became a sort of oddity to becoming an obvious anachronism around the time everybody realized that they didn't really want to shake hands anymore. So anyway, back in the 1950s, a bunch of people go to a conference. And when some people walk into a conference, they want to shake everybody else's hand. Like some people are friendly and they meet their colleagues and they shake their hand. There are certain people whose hands they don't shake because maybe there's some drama and they don't get along with some people, but they shake certain people's hands. So this person walks in and shakes 3 hands. They shake hands with this person, and this person. And this person walks in and shakes 2 hands. This person and this person. And notice that the number of hands each people shake is just the degree of that vertex. So if I call this vertex U, the degree of U is 2. That's the number of hands that person shook when they walked into the conference. This whole idea of shaking hands is so bizarre to talk about in 2025. I mean, now you walk into a conference and maybe you don't shake people's hand. I'm going to go to a conference next week. I'm not planning on shaking any hands there. I get along with everybody, but there's no need to shake hands. So suppose that they walk in and shake people's hands. Then there's a question. How many total handshakes took place? I know that this person shook 3 hands and this person shook 4 hands, but how many total handshakes took place? Well, each edge corresponds to a handshake. And the question is, how many, if I know how many hands each people shook, how many total handshakes took place? And that's why it's called the Handshake Lemma. So just like discussing the pigeonhole principle, it gets almost surreal when you try and describe it. The Handshake Lemma states this very useful, crunchy algebraic fact, and I will now just refer to it in graph theoretic terms, which is, if I add up the degree of every vertex, what I end up getting, the total sum, is 2 times the total number of edges. And here's why. So each of my edges is incident to exactly 2 vertices. That's a fundamental property of the edge, which means if I'm counting up the total degree of each vertex, a particular edge, like edge UV, gets counted as part of the degree of U and as part of the degree of V. So if I add up the degree of every vertex, I will count every edge twice, once at either endpoint, which means the sum will just be 2 times the total number of edges. And there's a nice combinatorial proof of that property. You could also prove this by induction. You're welcome to try. It wouldn't be so bad. Induction's great. But this is a nice, easy combinatorial proof of a very powerful property. And although the term Handshake Lemma is a bit of an anachronism, we do still use it and people still call it that. So we're just going to try and, conform here, we'll just call it the Handshake Lemma. It needs a name, and that is at least a distinctive name. What's interesting about the Handshake Lemma is that because it relates the degree of vertices to the total number of edges, and notice that because of this coefficient 2, there actually are constraints implied. So what this is saying is that if I sum up the degree of every vertex, the result has to be an even number because it's 2 times some integer. And we can actually use that to prove interesting things. So I may have spoiled the technique you need to use, but using the Handshake Lemma, try proving that it's impossible to have a 4-vertex graph with this distribution of degrees. There's no way you could ever make that work. Okay, so here's a question about edges. We know already that the minimum number of edges in a graph on n vertices is 0. I mean, we can't have a negative number, obviously, and we are allowed to have 0 edges. What's the maximum number? There has to be a limit, because I know that I can never have 2 different or 3 different edges between the same pair of vertices. So, of course, the minimum number of edges is 0, but what is the maximum number? Let's see if we can work this out. Here I have a graph on 5 vertices. Let's add as many edges as possible. Well, logically, if I look at, let's call this vertex V1. If I look at V1, the largest number of edges that can be attached to it would correspond to the case where V1 is connected to literally everything else. Okay, so it has degree 4. If I look at V2, same story. It'll have degree 4. And I can work out a way of giving every vertex degree 4. I think I now have it. I think every vertex now has degree 4. And I realize that I can use the handshake lemma to work out the total number of edges in the graph. So I know that the degree of vi is equal to 4 for all possible choices of I. So if I add up the degree of every vi, and that's for all vi, I'll just say for vi in the vertex set, then I'm going to be adding up, 4, right? Every vertex has degree 4, and because the number of vertices is 5, I end up with 5 times 4. And by the handshake lemma, that is equal to 2 times the number of edges. Okay, so that means that the number of edges in the graph, when I have the maximum number for this graph with 5 vertices, is equal to 5 times 4 all over 2, which is 10. There we go. Now the question is, can I generalize this to any number of vertices? And I think the answer is yes, because no matter how many vertices there are, if I'm working with a graph with n vertices, the maximum degree would be n minus 1. So I could just sub in n minus 1 in my derivation. The degree of each vertex is n minus 1. That means that the degree, when I sum them all up, it's going to be the sum of n minus 1. The sum will then end up being, well, the number of vertices is n, and each vertex has degree n minus 1, and that's going to equal 2 times the number of edges. In other words, the size of the edge set in that case, I guess I'll just cross this off, the size of my edge set in that case is going to be equal to n times n minus 1 all over 2. There we go. So that looks like the maximum number of edges of a graph. And we use the handshake lemma to derive that. Now there's a mild typo here, so I should have an over 2 there. You can see that there was supposed to be, rearranging the terms in the handshake lemma, there should be an over 2. But the result is correct. So the total number of edges in a graph with n vertices at most can be n times n minus 1 over 2. Now, it's worth it, I guess, because we might want to work with that graph for any number of vertices. That is, I might want to talk about the graph with the maximum number of edges, this number of edges for any number of vertices. It's good to give that a name, and we can do that. We're going to call that the complete graph. A graph on n vertices containing the maximum number of edges, that is to say n times n minus 1 all over 2, is called a complete graph, and it's denoted by this, so k sub n. So this graph here is K5 because it's got 5 vertices and every vertex has degree 4. If I look at Ki for various values of I, there's K1, it's got 1 vertex and 0 edges. There's K2, 2 vertices and only 1 edge. K3 is this pleasant looking triangle. K4 I've drawn as a square with a crossing X in the middle. And then K5 is the thing that we just created. What's interesting about complete graphs, and lots of other types of graphs as well, is that they can be constructed inductively, or you could view that as constructed recursively, with the following technique. If I want to construct K4, I go get a copy of K3, and then I make one new vertex and I connect it to everything. Notice that this is effectively the same as what I have over here for K4, although it hasn't been drawn as pleasantly. If I have K4 and I want to make myself up a K5, I add one new vertex and I connect it to everything. And notice that what I end up with is indeed K5. And so if you have a smaller Ki, you can always make Ki plus 1. Or you can make Kn by using Kn minus 1 and adding a new vertex to it. While we're on the subject, this is a bit of a tangent, but since I have this graph up on the screen, notice that when I drew K4 on this slide, I drew it with edges crossing, because I sort of like the idea of making each thing a regular polygon, so a triangle, a square, and a pentagon. But there is a way of drawing K4 such that no edges cross. If I chose to draw it in this clever representation, as a sort of tetrahedron, I guess, I can draw it in the same way. You can verify these two things are isomorphic. Well, these are the same graph drawn in two different ways. I can draw it such that no two edges cross. Now, the drawing of a graph is arbitrary. I can choose how to do it, but there are certain constraints on what I can draw. That is, there are graphs out there that I cannot draw such that no two edges cross. There are just too many edges. In the event that I can draw a graph such that no two edges cross, we call that a planar graph. And the drawing itself is called a planar embedding. It is a way of drawing the graph in the plane, so on a 2D surface, such that no two edges cross. And it's neat because K4 can be drawn, there is a planar embedding of it, so it is a planar graph. But not every graph has that property. Certainly K1, K2, and K3 do, because we can see that no edges cross in any of these drawings. But it turns out that K5 is not a planar graph. No matter how I rearrange vertices, even if I'm allowed to draw edges as complicated wandering curves, as long as an edge is a single continuous closed curve, there's no way of generating a planar embedding of any kn for n greater than or equal to 5. So K4 is planar, but K5 and up is not. Now, the study of planar graphs and how to draw graphs in the plane is important, but it's not something we're going to focus on in this course. But I thought that since we had the chance to bring it up, it's worth it to talk about it a bit. Now I want to talk about global properties. So a graph itself is a bunch of pairwise relationships, and what makes it so powerful as a modeling technique is the fact that you can create a graph in a given situation by only thinking of relatively local things. Like if I make a graph that represents a bunch of cities and connections between them. So for example, if I decide that each vertex is a city and each edge corresponds to maybe a road that links two cities together, all I have to do to build the graph is to look at each city and figure out which roads are attached to it. I don't have to think about more complicated questions like, if I start driving at city A, can I end up at city B? When I design the graph, I just make a vertex for the city, and within a relatively narrow horizon, I work out relationships between it and neighboring cities. Once I have the graph, though, I can use the graph to think about global properties. Things like, if I start at vertex A, is there a way to get to vertex B? And then once I know that there is, I can ask questions like, what is the fastest way to get there? What is the way that involves, I don't know, traversing the fewest other cities or the fewest edges? Or even further, something we're going to talk about in about, 12 lectures or so, questions like, suppose that it costs $5 to take this road and $10 to take that one, and it costs $100 to take this one and $17 to take this one, and so on. What is the route between vertex A and vertex Z that costs the least in total? That's a pretty powerful problem, and it turns out we can state that problem and solve it pretty naturally using graphs. So we're going to start on that road with this set of definitions. If I'm talking about a graph and I have two vertices, u and w, a path is a routing from u to w along edges of the graph such that the intermediate vertices do not appear more than once. So a path, everything along a path must be distinct, all edges and vertices. I can never do the same thing twice. It says intermediate vertex because there's a special case of a path where we are allowed to have a path that begins and ends at the same point, but all the vertices in the middle have to be distinct from each other. Formally, I'm going to use the term UW path for that. So a path between U and W, so from U to W, or vice versa, because in an undirected path, everything is symmetric. A UW path is a sequence of vertices, and I'll number them V0 through VK. And of course, if I was talking about U and W, then I assume that V0 is just U and VK is W, such that along this sequence of vertices, like V0, V1, any pair of adjacent vertices in the sequence are connected by an edge, and other than possibly the two endpoints, all of the vertices along the path are distinct. I'll show some examples of the case where they aren't distinct and what we do in that situation in a minute. Now, the length of a path, we have to define a convention for this, and I will define the length of a path to be the number of edges, the number of steps you take. The reason for this is because suppose this is vertex A and this is vertex B. Here is a path from A to B. This path has length 1. And it makes sense because I follow one link to get from A to B, so the length is 1. I want to argue that a path is allowed to have length 0. In other words, if I want to get from A to A, all I have to do is, nothing. I just start at vertex A and then I'm done. I don't travel any distance. So to me, it makes sense to call such a traversal a path of length 0. If I start somewhere and then go nowhere, I have traveled 0 steps. And so that's a path of length 0. And that means if I talk about can I get to A from A, the answer is always yes. I just stand still. If I have a path of length at least 1, so we can't talk about a cycle of length 0, if I have a path of length at least 1 that starts and ends at the same vertex, but where everything in the middle is distinct from everything else in the middle, then I have what's called a cycle. So a cycle is a way of walking around in a circle pretty much inside of a graph, where I never repeat any edges or vertices along the way. If a UW path exists, and maybe you can see, and this is a function of the drawing doing some work for us, but maybe you can see in this graph, if I pick any two vertices, there will be a path between them. In fact, there might be lots of paths between them. The path I've drawn here from U to W might not be the shortest one. That is, there might be a path that requires fewer edges, and there might be tons and tons of different variations on the path. For example, if I don't like E5, I could route my way around it like this. This graph contains quite a bit of redundancy in terms of paths. In some applications, we do think about the paths between two vertices, but we don't care that much which path specifically we use. We just want to know whether a path exists or not. I mean, if I'm planning a road trip between two places, so if I'm traveling from Victoria to Nanaimo, all I really care about in the initial stages of planning is there a way to drive from Victoria to Nanaimo? The specific choice of which roads I use, I don't care about too much if I'm just planning my trip. Later, I will have to look up the route that I follow. And so we often just want to talk about not give me a particular path, just tell me if one exists. So if a UW path exists, if there's more, there could be more than one of them, but if there's at least one of them, we say that W is reachable from U, and symmetrically that U is reachable from W. A path may have length 0, so if I want to travel from Victoria to Victoria, I just stay here. And so in that case, the path has length 0, and that means that U is, of course, any vertex U is always considered to be reachable from itself. Now, if I have two vertices where one is reachable from the other, I can now begin talking about, I guess, qualitatively different attributes of possible paths. There could be more than one path available, so what we'll do is think about, in the case where I care about the path with the smallest number of edges, which I sometimes do, but not always, there are plenty of cases where I might actually deliberately want to follow a path that requires a large number of edges, and that's fine. So there's no reason why the path with the smallest number of edges is always better, but in the event that we care about it, I will define the distance from U to W to be the length of the shortest possible path, the minimum length of a path between vertices U and W. This is only defined when W is reachable from U. There are applications we'll see in a few future lectures where we do consider the case where two vertices are not reachable from each other, and we sort of pretend that the distance is infinity in that situation. But for now, we'll just say that the distance only exists if we know the vertices are reachable, so it is actually some well-defined value. So in this case, it turns out the distance from U to W is 6. There is no way to get from U to W in fewer than 6 edges. Now, we actually haven't seen in this example a case where there are two vertices in a graph that aren't reachable from each other, but we'll see that in just a minute. So remember that when I talk about paths and when I talk about cycles, I'm not allowed to repeat vertices. Notice that if I start walking from U and I wander this sequence of edges here, I get to Z, and then I, for some reason, walk around in a circle, come back to Z, and then go on to W, I can get from U to W with that sort of circuitous traversal, but that isn't a path. A path can never repeat the same vertex twice. And because Z shows up at two distinct places along this, it is not a path. It is something else. There are a few places where we do want to consider the case where you are allowed to repeat vertices, but you're not allowed to repeat edges. That would actually be like in the bridges of Konigsberg. And so it's useful to give a name to this situation, but this is not, emphatically, it is not a path. Instead, the graph theoretic term is a trail. So a trail is like a path, but it is allowed to visit the same vertex more than once, but it is not allowed to repeat edges. So I'm not allowed to, once I've used an edge, I can't follow it again during a trail, but I am allowed to visit the same vertex as long as I arrive and leave that vertex via different edges every time. Now you might be asking, okay, but what if I wander around a graph and I do repeat edges? There is such a thing, and the general term we use for wandering a graph is a walk. A walk in a graph has no restrictions. You start at a vertex and you wander around using edges. You can double back if you want. You can repeat vertices if you want, and you end up at some endpoint. So for example, suppose I want to walk from, let's do this, we'll call this vertex A and we'll call this vertex B. Here is an example of a walk I might take from A to B. I go from A down here, I go here to U. For some reason, I then turn around and go backwards. I go back up to A, I go over here, I go here, I go here, I go down, I go back up here, I go over here again, and then I go here, then here, then here, then down, and then across. And I mean, you can see that this is full of duplication, but I could, if I wander aimlessly long enough, get to B, probably. And we call such a traversal a walk. It has no restrictions. We can wander as much as we want. We can repeat edges if we want to, whatever. And we don't need that very often in terms of stating the edges we follow. But the idea that, of course, I am free to wander aimlessly in a graph, that's possible. I'm allowed to do that. Usually, though, we care more about paths. And occasionally, we care about trails, which relax the definitions a little bit. Okay, so now let's talk more about reachability. if I have a graph where any two vertices are reachable from each other, so in other words, if I pick any two vertices I want, there's always a path between them, then I have what's called a connected graph. A graph is connected if for every pair there is some path between that pair of vertices. And of course, this graph here is connected. And I will observe that connectivity is something that's very natural if you have a good drawing. So you could probably glance at a graph and just tell me by sight whether it's connected or not if you have a good drawing. But don't be fooled. The reason it's so easy is because the drawing is good. The person who made the drawing wanted you to see that the graph was connected. So what if the graph isn't connected? So here's a graph that isn't connected. Now, the way that you'd theoretically justify that it's not connected is you show me some pair of vertices where no path exists. So you could demonstrate that there is no way to get from Z to Y. It's impossible. You can't follow any edges to get from Z to Y because they're on sort of separate islands. If I wanted to prove that this graph was disconnected, I'd probably fixate on this vertex here. So if I say here's a vertex A, because vertex A has degree 0, even the most skeptical observer would agree there is no way you're getting anywhere from vertex A, and therefore the graph, as long as it has at least one other vertex, must be disconnected. So I mentioned a minute ago that it looks like the graph is full of a bunch of separate islands. So let's look at them. Here's an island here. Here's one down here. And I notice if I consider each island in isolation, each island is obviously a connected graph if I just ignore all the other islands, because I broke the graph up into connected pieces. And often when you have a disconnected graph, that's exactly what you do. We can partition any graph, connected or not, into connected components. So each component of a graph is a connected thing. I want to say subgraph, but maybe we haven't heard that word yet. Each component of my graph is connected. If I have a connected graph, so here's a connected graph, this has one connected component. It's just one big thing. This disconnected graph breaks into, I guess we've got 5 connected components. So as I said, it's really tempting to look at this and say, oh, that was obvious. Anybody could look at this drawing and decide that it has 5 connected components by just circling them. Yes, it is obvious, but the reason it's obvious isn't because connectivity is simple, it's because the drawing makes this easy. You've been served up on a silver platter the task of finding connected components. It's easy for you. It's very easy to demonstrate that it's the drawing doing the work. So it's very easy when you see these good drawings, not just for connectivity, but for path finding, to think, oh, it's easy to find a path. I can obviously find a path from A to B. I just walk like this, because your brain is so good at pattern recognition and the graph is small enough that you can just see the right path on sight. The same as if I give you an array of 5 elements, so 187, 6, 17, 10, 225, here is an array of 5 elements. Could you sort it for me? Well, of course you could. You wouldn't need to use an algorithm. You would just write it out in sorted order. Because for a certain length of sequence, your brain can do all the work subconsciously. But be careful. Don't assume that that means the problem is easy. We already know that sorting isn't easy. We know that sorting requires, in the general case of comparison sorting, at least n log n comparisons and so on. So here's how I'll justify that. Here's a graph. Is it connected? I'll wait. I have some tea here that's gotten cold over the last hour. I'll just have a sip. Oh, that's still pleasant. It is cold, though. So is the graph connected? Let me know. I hope you can see that it's not a trivial task. And this is not even a very big graph. Remember that the graphs I'm drawing on these slides that have like 10 or 12 vertices are toy examples. The graph problems we find ourselves working with, the ones that we're going to work with, maybe 2 lectures from now, the ones we're going to be talking about, are going to be graphs that have maybe 1,000, maybe 1,000,000, maybe 1,000,000,000 vertices. We need the ability to divine attributes of graphs that are non-trivial, even when the graph is huge and really complicated. And by simply choosing to draw this graph in a very obnoxious way, I hope I've shown that the problem of deciding if the graph is connected isn't really as easy as eyeballing it. So was the graph connected or not? Well, let's find out. It turns out that the graph was actually 2 connected components, but I just scrambled them up in such a way that doesn't make that obvious. Now that I know that one of the components is ADGH, I could go backwards and work that out. So here's A, here's D, here's H, and here's G. And if I just isolate the edges between those 4 things, so there they are there, and finally this one. What you'll notice is that, so what I've done now is simply colored in the edges that connect A, D, G, and H to pairs of each other. Notice that all of those vertices have no edges left. In other words, there is no edge that connects any of A, D, G, or H to the outside world. All of the edges stay stuck within that collection. And that's a sign that A, D, G, H is a connected component. There's no way of leaving it, which means I found everything in the component. And that means all the remaining vertices are unreachable from A, D, G, and H. So I must have at least 2, and it turns out I have exactly 2 connected components. I hope this is a good piece of evidence that the drawing is doing a lot of the work for us. It's good to have nice drawings. We should strive to produce nice drawings, and I will attempt to give you nice drawings in all the cases except where I'm deliberately testing. I mean, I could give you this on a midterm and say figure out if it's connected, because we're going to spend an entire lecture on connectivity testing to show algorithms to find that in cases where you can't eyeball it. Outside of that, though, I do endeavor to draw graphs nicely because it's helpful to understand what's really going on. So keep that in mind. The drawing does a lot of work for us, and we should be grateful to have nice drawings. And we're going to study algorithms to find paths and test connectivity. Because, of course, with a nice drawing, if I want a path from C to F, I can just color it right in. But if I have the ugly drawing, finding a path from C to F, it would be very easy to get lost if I just try wandering around in this representation. So we're going to study algorithms for pathfinding and testing connectivity and finding connected components in future lectures. Coming up, I think 3 lectures from now, there will be 2 lectures on pathfinding, or on algorithms that can be used directly for pathfinding. Later, we're going to have 1 entire lecture just on connectivity tests, and then connectivity will come up again a few other times, and pathfinding, in the case where we're doing an optimization form of pathfinding, will come up in 3 lectures, I don't know, about 12 lectures from now. So we're going to spend a lot of time talking about pathfinding and connectivity. They are not necessarily easy problems. Okay, here's a word that I already spoiled. I used it by accident when talking about connected components. I want to talk about a subgraph. So consider this graph H. Notice that the vertices of H and the edges of H are all sort of extracted from my graph G on the left. So H is what's called a subgraph of G. A subgraph is a graph whose vertex set is a subset of the other graph. So H's vertex set is a subset of the vertex set of V, and the edge set is also a subset of the edge set of the original graph. But H is a graph. So there is one more restriction that's sort of implicit, which is that, yes, the edges in H are a subset of the edges of G, and the vertices of H are a subset of the vertices of G, but in addition, none of the edges in this set can be edges, I guess I should say it the other way. All of the edges in the edge set of H must connect vertices in H, because that's a requirement of a graph. So I wouldn't be allowed to add this edge to the edge set of H because this vertex isn't part of H. So that's an implicit requirement when I say that something is a graph. The edges have to connect actual vertices of that graph. When I have those conditions met, H is a subgraph of G. So every vertex and edge in H must be contained in G, but H is not required to contain any particular vertex or edge. So that is, there are plenty of vertices of G that H doesn't contain. In general, a subgraph can have any number of vertices as long as they're taken from the original graph, and same thing with edges. I could have a subgraph that contained all of the vertices but none of the edges, and I could have a subgraph that contained none of the vertices or none of the edges. It could actually just be an empty subgraph. Both of those would be considered subgraphs. There are special types of subgraphs, and there's one particular special type of spanning subgraph we're going to see in the next lecture that's a really big deal. In the meantime, a spanning subgraph is a subgraph where every vertex appears. So in this subgraph H, notice how H contains every single vertex of G. It doesn't contain all the edges, but it does contain all the vertices. Now, a sort of complementary thing is what's called an induced subgraph. An induced subgraph is one where you take some collection of vertices and you bring with it every edge that connects within that collection of vertices. So in other words, I choose some arbitrary subset of vertices, and the edge set of my subgraph, the induced subgraph, would be all of the edges that go with those vertices, where both endpoints of the edge are within the vertex set that I chose. And we'll use spanning subgraphs and induced subgraphs quite frequently, especially as particular form of spanning subgraph. Now, one topic I left out at the very beginning that I said I would come back to is the idea of having edges have an inherent sense of direction. So in our undirected graphs, an edge simply connects two vertices. There's no inherent order or priority to that. But there are cases where what I'm modeling with the graph does imply some sense of order. So for example, if I used a graph to model connections between things, like connections between cities or connections between different parts of town, then I could say, okay, draw an edge between two things if there's a road road between those two places. Or I could have each vertex be an intersection and each edge be a road. But I realize there are cases in real life where things are only one way. What about one-way traffic? Maybe I want to be able to encode a direction into my edges. If I do that, then I require that a direction be associated with all edges. In other words, it's all or nothing. Either every edge has a direction or no edges have a direction. In the case where they do have a direction, we have what's called a directed graph. Previously, we were talking about undirected graphs. So a directed graph is a graph where every edge has some associated direction, and edges are therefore formally considered to be ordered pairs rather than unordered ones. So in this case, this edge is the pair UW. And it's an ordered pair because I care about the fact that U is the source and W is the destination. The edge goes from U to W. And so we have a few ways of saying that. As I said, you could say from U to W. You could say that U is the source and W is the destination of the edge. In general, when we talk about directed graphs, we'll still write edges this way. Although unlike in the undirected case, this edge UW and this edge WU are two separate things. UW is an edge from U to W, whereas WU is an edge from W back to U. So the ordering makes a difference if our graph happens to be directed. And it will be clear whether edges are directed either because you will be told that the graph is directed or you will see that in the drawing of the graph there are edge directions. Now, since direction is significant, that means that edges pointing in opposite directions have to be distinct from each other. That is, this is the edge UW, but the edge WU is a different edge because it points in a different direction. And that means that we are actually allowed to have edges, I guess I've gotten ahead of myself, that means we are actually allowed to have edges that point in both directions simultaneously. So I'll come back to that when the slides are ready for me to talk about that. In some sources, you will notice that edges in directed graphs are called arcs. So the word edge means undirected and the word arc means directed. I think that's a bit of an old-fashioned thing, to be honest. I do that occasionally myself. I let it slip occasionally. But I tend to accept what seems to be the contemporary norm, which is simply that it's clear that you mean directed edge if your graph is a directed graph, because every edge in a directed graph has a direction. So sometimes I say directed edge when I talk about edges in a directed graph, but in general, if we're talking about a directed graph, we just call the things in it edges, and it's clear from the context that we're talking about directed edges. The word arc, as I said, is often used by some sources, but I generally don't use it. Although if I do, here's a definition of what I mean. I mean just an edge in a directed graph. It's also important that because edges now have directions, the terminology of adjacency and neighbors needs to be elaborated a little bit. So here, vertex A has this edge coming into it from U. It's possible, therefore, to get to A from U, but I can't get back. Notice how if I want to get to U from A, there's no edge connecting from A to U. So I'll talk about the idea of paths in a directed graph in a minute, but in the meantime, I want to differentiate between the two different kinds of neighbors a vertex can have. Notice how I have this one edge that is inbound into A. And so I'll think of U as being an inbound neighbor of A. And similarly, I'll want to differentiate the degree of the vertex by the direction of the edge. In this case, the in degree of A is 1, because A has one inbound neighbor, which is vertex U. On the other hand, there are edges from A to B and to C. And so B and C are outbound neighbors of A, and the out degree of A is 2. Now, here's the thing I wanted to say about it 2 minutes ago, which is because the direction of an edge is significant, these two pairs are distinct. So I can put them both in my edge set. That's fine. And that means that by my definition of simple graph, this is allowed. In a directed graph, you are allowed to have edges pointing in both directions, but only one of them. So I'm still not allowed to have multiple edges from W to U or vice versa. But I am allowed to have an edge pointing in both different directions because those are separate edges. There aren't actually duplicates happening here because those are two separate things. And we often see that in directed graphs. It's important that we have this privilege because you might have thought a minute ago when I said that either every edge has a direction or no edge has a direction. It's all or nothing. You might have thought that's unreasonably restrictive. What about cases where I only want some edges to have a direction? I want there to be a bidirectional connection between most vertices, but some edges are one way. Some edges have a direction. That's like with one-way traffic. Many roads are not one way. If you want to get the effect of undirected edges in a directed graph, just add both directions. So in other words, a directed graph actually gives you more features than an undirected one. So if you want some undirected features in a directed graph, you can do that by just doubling everything up, by having both directions of an edge present. What about paths? Okay, so a general rule of thumb is if you're working in an application where the graph is directed, so if somebody has seen fit to model their problem with a directed graph, then directions should always be respected. There are very few cases where we ignore the directions of directed edges, and we do that only very carefully after careful consideration, which means any definition we apply to a directed graph should attempt to take into account the direction of the edge, and paths are one of those. So in a directed graph, when we say a path in a directed graph, we are referring to a directed path. I will just say path because in the context of directed graphs, it's clear what I mean. A directed path must respect edge directions. Notice that in this graph, I can reach z from y. There is a yz path. It's highlighted, you can see it. There actually isn't a path from z back to y. I can get from y to z, but I can't get from z to y. Notice that the out degree of z is 0. There is no way to leave z once I get there. I get stuck, pretty much. And that means that reachability isn't symmetric. In an undirected graph, where there are no directions, if I can go in one direction, I can go in the other, because edges can be traversed either way. In a directed graph, it's possible that reachability is only a one-way thing. So I can go from y to z, but I can't go backwards. And that has some implications. And one of them is that when I talk about connectivity and connected components, the definition that I had for undirected graphs doesn't really generalize. Because in an undirected graph, it's easy to talk about if y is reachable from z, then the converse is also true. Z is reachable from y. But that's not true in a directed graph. I could have a one-way relationship. Now, I could also talk about a directed cycle. And just like how a cycle is a type of path, a directed cycle is a type of directed path. So the concepts of connectivity and connected components, as I said a minute ago, can be generalized. There's a way of talking about a type of connectivity in directed graphs, but I won't talk about that just yet. It deserves a large segment of a lecture to talk about. So we're actually going to have a separate lecture on connectivity after we've learned some other things. The key thing to know right now, as I said, is that reachability isn't symmetric. Just because I can go from y to z doesn't mean there is necessarily a way to go backwards, but there could be. So if I have a directed cycle, for example, and I name this vertex x, notice how I can reach x from y and I can reach y from x, because there do exist paths that go in both directions, but they have to be separate paths because they go in different directions. Now, we're just about done with our long set of graph-related definitions, but before I finish the lecture, I guess we do have to solve the problem of the bridges of Konigsberg. And so we now know enough about graph theory to solve this problem, to walk through Euler's solution to the original graph theory problem. Sure, it does involve a multigraph, but we're going to see that we can apply a lot of our insights about simple graphs to multigraphs as well. So the question really of can I cross each of the 7 bridges in one walk is actually a question that amounts to, is there a trail in my graph that traverses every edge in this multigraph? And remember that a trail can start and end at different locations, so it doesn't matter if I end up stuck on the opposite side of town. The question is, can I traverse every edge in the graph in one trail without repeating any edge? Because in a trail, you're not allowed to repeat edges. And the answer, it turns out, is no. So Euler's foundational graph theoretic result was that it is not possible to cross all 7 bridges in Konigsberg on one walk. Now, in modern-day Kaliningrad, there are more bridges, and so it might be you can now cross all of the bridges in one walk, but back in 1736, it wasn't possible. But how do you prove this? Like, what do? You've drawn this clever abstraction. How do you show that it is impossible? Because proving that something is possible tends to be relatively easy. You just show an example of it. So if there was such a walk, all I would have to do is show one to you, and that would prove it. But there isn't one. How do I prove that something doesn't exist? We've seen before that that tends to be quite a difficult thing to do. Here's what we do. It turns out that it comes down to the degree of each vertex. Notice that every vertex in the graph has a degree which is an odd number. So this vertex has degree 5. All of the other vertices have degree 3. And this is going to be a problem because let's think about what our trail has to do. Suppose I pick a starting point and an ending point. So our trail is going to start here and end here. Every other vertex, it has to enter and leave maybe more than once, but certainly every time it enters the vertex, it leaves it. Because if this vertex is in the middle of the trail, then I don't stop there. If I go into the vertex, I have to leave it. Okay, so how is that going to work? Well, let's say I enter, we'll use this vertex as an example. I enter it along this edge, and then I leave it, let's say, along this edge. And then later I come back to it along this edge, and then I leave it along this edge. That's fine, I can do that. But then I have to enter it again along this edge somehow. And that's not going to work because once I'm there, I'm trapped. How do I leave it without using an edge I've already used? It turns out that the parity of the degree, whether it's odd or even, has an impact on whether a solution exists. So that's what Euler proved. He proved that if a vertex of odd degree appears in a trail that traverses all edges, that can be fine, but only if that vertex is either the beginning or the end of the trail. It isn't possible for a vertex of odd degree to appear in the middle of a trail or to not be the first or last vertex. That is, if this is the first vertex, sure, I can come back there once, but it has to be either the beginning or end if it has odd degree. Here's a different multigraph where only two vertices have odd degree. What I want to show here is that having an odd degree doesn't inherently break anything. It's only if you have so many vertices of odd degree that you can't have all the odd degree vertices be the beginning or end of the trail. So there is a way of walking through this hypothetical pseudo-Konigsberg where I do cross every bridge exactly once on a trail. And that's because I do have odd degree vertices, but all of the other vertices besides these two are even degree. Okay, so we'll just look at the trail. So suppose I start over here, and then I walk down this edge here, and then I cross up here, and I come back to my starting point. That's fine. I can still leave via that edge. So I do that. And now I've left my starting point forever. I clearly can never come back because all of the edges have already been used. And then I walk around here. I actually reach my end vertex, but no big deal. I can leave it again. And then I walk back to the end point, and I finished my trail. So in this graph, I was able to cross all of the bridges, even though there are two vertices of odd degree. The slides had a few words to say in the meantime, but I'm actually just going to I'm going to skip that. You can look at those slides later. That's basically what I'm about to say anyway. Essentially what's going on is, if I consider the vertices in the middle of my trail, I know that I'm not going to end on those vertices. So every time I enter the vertex, I have to also leave, which means that the edges attached to the vertex have to come in pairs. Every arrival must correspond to a matching departure. And that's fine. If the vertex has even degree, then it may be possible to do that. Now, there could be graphs out there where all vertices have even degree and no trail exists, for all I know. All Euler proved was on that particular graph, because every vertex has odd degree, there cannot be any trail that exists that crosses all the bridges without repeating any of them. So in the Konigsberg graph, all four vertices have odd degree, and we know that an odd degree vertex must either be the start point or the end point of my trail. But no matter how I choose my start and end point, the other two vertices left over always have odd degree. So if these are vertices that I see in the middle, that means every time I enter them, I have to leave them. But if there's an odd degree, that means that the number of arrivals has to be greater than the number of departures, or vice versa. And that's only permitted if I'm working with my start point or end point. And so in that, Euler was able to prove that it's impossible to cross all 7 bridges of Konigsberg in one walk. And he did that inadvertently founding the discipline of graph theory. And notice that once we had all the graph theoretic terminology, if we had started with this multigraph after already learning about vertices and edges and degrees, the problem is relatively easy to state and theoretically classify and solve. That is, we know we're talking about degrees, and we know what it means to traverse an edge and use a trail. And that was part of the amazing thing Euler did. Back then, these types of abstractions weren't as clear to people. We're very good at abstraction now, but that was still relatively new at the time, the idea of boiling the problem down to such an abstract representation. And the fact that graphs provide that abstraction is one of the things that makes them powerful. And as we're going to see over the next few lectures, the other thing is that despite being quite an abstraction, despite omitting a lot of details of a problem, the idea of modeling something that we might see in real life or some theoretical construct using a series of pairwise relationships does give us very powerful modeling. It allows us to say quite a bit about a problem, to generalize from very local conditions like what bridges are attached to vertex X to global things like, can I wander around the city in a certain way?